a solution guide to the topic on the normal curve, continuous probability distributions. So this is our practice test. Question 1, find the area of the indicated region under the standard normal curve. So when they're calling this a standard normal curve, remember the word standard for the normal curve means that the mean is equal to 0 and the standard deviation is going to be equal to 1. We are given over here, this means it must be a z-score. I guess you see the mean right there is 0. And they want the area above this marker. So what this is going to look like, it's the probability, the area that x or z if you want it, but yeah, usually we call this the area is greater than negative 1.30. So that's what we're going to enter in over here on our calculator. We'll go to our distributions. We'll go down to normal because it is a normal curve. Our mean and standard deviation by default are 0 and 1. That's perfect for us. And then we just have, notice the tool we've got is x less than or equal to 0. So we got to change the tool to the x greater than or equal. Now this has an equals. It really will give us the same thing as if it doesn't, because on a normal curve to be actually equal to one pot, because it's just a single line, a line has no width, is always 0. So we get a little sloppy here, but this is the one we want, and we can see from the visual we're getting the area above, and then we just match it. We put in our negative 1.3 and we hit execute, and we see that our curve is about the same, right, for the area. And there's our area, 0.90319, 9031. That gets rounded up. There's the 2. It's this one right here. Okay, so that was question number 1. That's all there is to it. This one, find the area of the indicated region under the standard normal curve. We're going to do the same thing. It's still got the mean of 0. The only difference here is we are getting the area between two values. So between two values, this one and this z value here, this is going to look something like the probability negative 0.45 is less than x is less than 2.11, something like this. So when we come to our calculator, the tool we need to use is the between tool. I don't know if it's really a separate tool or just a version of the tool, but you can see we've got our between x just like here. And we put in our two values, negative 0.45. You don't have to put that 0, but it's maybe sometimes helpful because of the decimal. And then we put in 2.11. We hit OK. OK. I guess it's, oh, there we go. I guess maybe it already did. And you can see that we're matching about what the area of our picture is. We're getting the right shadings and everything. So our answer is going to be over here, 0.6562, 6562, and we can see from all the choices that's the only one there. You also maybe just could have eyeballed it. It certainly can't be this one if you remember, because it's the whole area is 1, so 1.3 is not going to fly. These 0.3s, that's about 30%. This looks like more than 30%. So even just looking at the picture, you could almost pick this one out of the lineup. But we want you to know how to use the calculator to do that. All right. Similar thing for this question 3. Use a standard normal table. Now we're not going to use the table because we have this calculator here. We might not match this exactly because the table has to do some rounding, but let's just see how we would do this. The lengths of pregnancies of humans are normally distributed with a mean of 268 days and a standard deviation of 15 days. So notice we are not working with the standard normal anymore. We have a mean that is different than 0 and standard deviation different than 1. But we can go forward. Find the probability of a pregnancy lasting 250 days. So remember, probabilities are always numbers between 0 and 1, so that's why they're all decimals. But we do the same thing here. The thing we have to do here first is we have to go back and change our mean and standard deviation, 268 and 15. So the mean is 268, standard deviation is 15. And so now we're not working with z-scores. We've got actual measurements. So these are how many days the pregnancy lasts, lasting less than 250 days. That means 250 days is the big number. This is less than, so we're looking at x less than 250 days. Okay, so our setup will look like this. We want the less than, and our calculator sort of defaults to that, the less than side. And we put in our 250, and we get 0.115, 1 rounded. So that's option B. Okay, with the mean of 268 days. Now, if you had chosen the wrong one, let's see if that even matches. This is greater than. You don't even match the answer, so hopefully you're doing that. But again, this one definitely less than. But okay, and it's just as simple as that. Okay. Number 4, an airline knows from experience that the distribution of the number of suitcases that get lost each week on a certain route is approximately normal. They lose on average 15.5 suitcases, and they have a standard deviation of 3.6. What is the probability during a given week the airline will lose less than 20 suitcases? Okay, again, we come back here. It's still less than. So the probability that x is less than 20. Remember, x is our random variable, so it's the number of suitcases in this case, less than 20. And so we come back here. We have to reset our mean to match the number we were given here, 15.5, and then 3.6. 15.5, oops. Just 15.5, and then 3.6. We'll do a check here. That's what we got. We'll go okay, and then we want less than 20 suitcases. So again, we make sure we're in the less than tool, which is the default. We put in our 20, and it shows us, and 20 is more than the mean, right? So the mean's right here. 89%, 80.8944. So that's going to be A. And again, you can kind of think, well, it's got to be, since there's less than 20, 20 is bigger than the mean, so you're certainly going to have at least 50%. If so, just thinking through this without even doing the calculator, you should say, well, it's got to be more than 50% because you're losing more. This is well, if you draw it, your mean is 15.5, and 20 is going to be bigger than that. So yeah, it's got to be more than 20. You could just say, yeah, none of those will fit, and there we go. Okay. Number 5, assume that the heights of women are normally distributed with the mean. Again, you're just using the same tool. We've got a mean and a standard deviation. You could read this if you like. Cheerleaders for the local professional basketball team must be between these heights, 65.5 and And 68, if a woman is randomly selected, what is the probability that her height is between these? Okay, so we will go ahead and put this in. Again, we just change our mean and our standard deviations to what they are, 63.5, so 63.5, and then the standard deviation is 2.5 inches. We want the between, and so we choose that icon, and we get 65.5 is our lower end, our upper end is 68. So it's going to be 17%, right? 17.5, 0.1759. Let's see, did I do that correctly? 65.5, 63.6. Let me check. Oh, 63.6. So I had a little error there. I'll bet you I still probably could have gotten the one close enough to it. But, yeah. Wait, I did it again. 63.6. What is that? 63.6. That makes a difference. And we're going to see. Now I go back, get my between, and I want it between 65.5 and 68. Even a little decimal off can cause some problems, so 0.1844. There we go. That's looking better. Again, I would have chosen this one anyway, but I encourage you to keep going so you can match these, because maybe I was making a bigger error, right? So that was just an entry error. I was putting 0.5 instead of 0.6, but it makes a difference. Okay. So now these next ones, we're going to be given a percentage, and we're wanting to find, values. Okay. So for this one, assume the heights of women are normally distributed. This is giving some different values, but again, it's just an assumption. 65.4, standard deviation 1.5. Find Q3, the third quarter that separates the bottom 75% from the top 75%. So you could do it either way. You could either do it less than 75, or you could do it greater than 25, but you'll find that value that's right on the boundary is what we're looking for. Okay, so, and I'll show you both ways will work. Again, what we have to do is come back and set up our mean and our standard deviation. So we go back. In this case, it is 65.4, 65.4, and standard deviation 1.5. Now, one way to do this is we want to do the less than. We 75%. What's 75% less than, right? That's a quartile. Oh, not, sorry. I put it in the wrong place, but I said, wait, one can't do it. So I'm just going to come over here. Well, it won't let me. Let's see. Oh, there we are. 0.75. That's what we want. Okay. We want, we're given the area, so that's 66.4. 66.4 right there. So I'm going to go ahead and 66.4. What I'm going to show you is we could have also said, well, it's the top 25%, right? So we could have used this tool, and then in here we put 0.25, and you're going to see we get the same thing. 66.4. It's the same boundary point, but now notice this is shading the top half. It works both ways. Okay, so that was question number 6. Assume the heights of men are normally distributed with a mean. So again, you come through here, you just want to highlight these or underline them, the mean and the standard deviation, right? Those are the two important things we're going to need. If the top 5% and bottom 5% are excluded from an experiment, what are the cutoff heights to be eligible for this experiment? Round your answers to 1 decimal places. So again, we're going to have, I don't know why I've got all this paper down here, but well, let's sort of a normal curve, right? So we want to exclude the top and the bottom 5%, top percent 5%, bottom 5%. So what's in the middle? That's 10% total off the ends. So we're also could look for 90% in the middle. Okay, so again, you can do this twice, and I'll do them both, and you'll see that you'll get the same answer. What are the cutoff heights to be eligible for this experiment? Okay, 70.1, 1.1. First thing is we have to enter our, I forgot already, 70.1. That's what I thought it was. 0.1 and then 1.1. Okay. You could say, okay, the less than part is going to be 5%, 0.05. So the one cutoff is 68.3 to 1 decimal places. 68.3, so you have to be at least that height. Yeah, you do it. I'm just going to go like this, less than X, and then the higher end would be to come over here and say, okay, we want to be this one, the greater side, and we want to see what that looks like. The top 5%, 0.05. That's also going to get excluded. So that's up to 71.9. 71.9. So you could do that. That's exactly what the question's telling us to do. However, you could also come here and say, let's find the middle, and you're going to see we'll get the same values. We want the middle 90%. We want 90% to be in the middle. And you see we got the same two values, 68.3, 71.9. Same values in one fell swoop, but we had to think we got what we don't want, but that boundary point is going to be the same for both of them. However you want to do this, whatever makes the most sense to you. Okay, so that's number 7. A tire company finds the lifespan for one brand of its tires is normally distributed with a mean of 47,700 and a standard deviation of 2,000 miles. If the manufacturer is willing to replace no more than 10% of the tires, what should be the approximate number of miles for a warranty? Now, I did this before, and I kind of did it. I didn't do it quite right, because what you got to think of is when would they pay out on this warranty? They would pay out on the bottom 10% that don't make it to this whatever the cutoff is, right? So no more than 10%. We're looking. We can't. These tires that are. This here has to be 10%. It's not the top 10%. You want to cut off the bottom 10%. That way, because these are the ones we'd have to pay on. Because these tires did not make it as long as they should have, or as long as these. So that's the key part of this question. But then the rest is, let's just put in 47,700 and 2,000. And then we want no more than 10% payout, so that's the bottom 10%, which is the default. And again, we put in the percentage over here, and we're going to find our value there. So 0.1, and so that's 45,136. They're probably going to round it, 45,140. They do. Although 136, they rounded up to 40, they'll actually pay a little bit more than 10%. Who knows how many. But actually, we could figure that out. This little rounding error, I just like to make things real. 45, 140, 45. Let's clear. 45, 140. Let's see how much that rounding actually cost them. I guess that's still 10%, even if you round it. Okay. See, it didn't make that big of a difference. Okay, thought it might. Assume that the heights of women are normally distributed with a mean of 63.6. Getting their data from different places. Standard deviation, so remember, those are the two values we need. If 100 women are randomly selected, so we're doing a sampling here, right? We're randomly selecting. So find the probability that they have a mean height greater than 63 inches. And so this is referring to the sample. So now that's when I need this paper, right? So we have for number 9, we're given the population mean as 63.6. The population standard deviation is 2.5. So we're sampling with an n equal 100. Remember, the mean is the mean, so the sample mean is going to remain 63.6. These are always going to be the same, but the sample standard deviation is going to be 2.5 divided by the square root of n. I love when they do 100 because I can do that in my head. Square root of 100 is 10. When you divide by 10, you move the decimal over one spot, so this is going to be 0.25. You can also just plug in the calculator if you like. So this one's going to be 0.25. So now, this is just like we've been doing. This was the only new step, was to calculate the sampling standard deviation, the sample standard, yeah. And where are we? We're up here. So now have a mean height greater than 63 inches. So 63 inches, the x is greater than that. So x has to be greater than 63.0. So that's what we look at. We're going to put this as our mean, this as our standard deviation, and then we will be all good. Here we go. 63.6, and be careful, it's not 2.5, it's 0.25. 0.25 for our standard deviation. Now, if you put the other one, the 2.5, I'll bet you that answer's there, but we're going to make sure we don't get that one. And then we want x is greater than, so we choose the greater than side. The shading is to the right, and then we've got our greater than, and we put our 63.0, and and we see it here, right? Here's 63.2, here's 62.8, 63.0 is right there, and this is all the percent greater than. And notice this is below the mean, so it includes the mean, right here. So it's got to be bigger than 50%. In fact, a lot bigger than 50%. Now, I'm just going to back off and show you that you have to be careful here, because if we back it up, if we put in the wrong standard deviation, the 2.5, I'm going to bet that answer is here. We do have to switch over to x greater than, and we put in oops, 63.0, 0.59. Oh, I'm glad. So I guess if you made that mistake, it's not there, right? Wait, did I get everything else right? 63.6, 2.5. Okay, so at least the test makeup is being fair with us, because if you put the wrong thing, you're not even getting close to any of the answers. So that's kind of good. But on the, on a test, I would put this one in here, because that's going to be a mistake that gets made. So just be careful. Remember, this is sampling, and the rest of these are going to be sampling. Assume that the heights of women are normally distributed with a mean of 63.6, a standard deviation of 2.5. If 75 women are randomly selected, find the probability they have a mean height between 63 and 65. Very similar, but again, for this one, for number 10, we're going to have to come down here, and we know that the population mean is the same, 63.6. Population standard deviation is 2.5. This time, the n for number 10 that we're working on is 75. So again, our mean of our sample is 63.5. The standard deviation of our sample is going to be 2.5 divided by the square root of 75. Now, we don't really need to remember, I keep forgetting, we could actually calculate this in here. So I'm going to go ahead and do that. So we're going to go back. We'll put in our mean, actually 63.6. We got the same mean. Here we're going to put in 2.5 divided by square root of 75. Isn't that cool? I don't know. I get impressed by little things. And then I'm going to get it anyway, so I didn't have to go back to the other calculator. I kind of like that, 0.2887. But I get great accuracy there. I don't, I'm not rounding or anything. And so now that I've got that, I want to find between 63 and 65, again, of the sample. And so I just go to my between tool and I enter my values. 63 is the lower end, 65 is the upper end, and I'm getting a between, and that's 98% of everything. And so that's going to be this one right here. And again, you could check if you use the wrong standard deviation, one of these answers might match up, it might not, but that's how we do it. Okay, one more, two more, three more. Okay, let's keep going. Assume the salaries of elementary teachers, school teachers in the United States are normally distributed with a mean of 32,000 and a standard deviation of 3,000. If 100 teachers, so these are all going to be sampling, are randomly selected, so that's a sample, find the probability that their mean salary is greater than 3,200. So again, you might not even need to write these down anymore, right? You could just say, okay, sampling distribution. So let's change our mean. It's 32,000. In here, we're going to put the standard deviation as 3,000. The sample is the n is 100. So I could just enter that in here, 3,000 divided by square root of 100. Save ourselves some time, but I'm getting all the values as I enter them. I can check them. Okay, that's 300. I've got the right value now, and we want greater than 32,000. So I have to change to the tool that has the greater than. X is greater than 32,000. Come on. 32,500. So I come over here, 32,500. And I can see the greater than part here, 0.0477. I must have put something, it's looking like this number, but my number's not that. I would have got 0.0478. Let's see, what did I do wrong? 32,500, 3,100 teachers. Did I have 32,000 is the mean, 3,000 divided by 10 is going to be 300. It may be that they're looking at the table, and the table's going to do some estimating. So we're as close as we can get. So that's the thing, is we get a more exact value. Okay, I'm going to just stick with it. Yeah, I know it's a little, but it's close enough within the 4th decimal place. The mean annual income for adult women in one city is 28,520. The standard deviation is 5,800. The distribution of incomes is skewed to the right. Okay, so it's skewed to the right. It's going to look, so it's not normally distributed, something like that. Find the mean and standard error. That's the standard deviation of the sample, of the mean of the sampling distribution when using random samples of size 42. Remember, as long as the sample is 30 or larger, we don't need the original to be normal. The sampling will be normal. Okay. The cool part is how that central limit theorem works. The mean is always going to stay the same, and notice you can't get that wrong because they're all the same, but the standard deviation changes. Remember, it's going to be 5,800 divided by the square root of 42, and we're going to get whatever value that is, right? We don't have to do anything more after that, so we can just go back and go to our regular calculator. Use the TI calculator if you want. 5,800 divided by square root of 42, and we get 894. Rounding 895. It's this one here. Okay, so this one we're just finding the standard. So we just have to know standard error is the same thing as standard deviation. They call it the standard error because in statistics, it's okay to have error as long as we know what that error is. So it's the amount of error, deviation from the mean. Okay, one more. The weights of people in a certain population are normally distributed. A mean of 152 pounds, standard deviation of 20. You'll see, you always get this. Find the mean and standard error of the mean of the sampling distribution when using random samples of size 3. Now, let's see. Since the population is normally distributed, we can have a size of any, the sample size of any size, and it will also be random, will be normal. Notice they give us the mean is always the mean. So sometimes if you look ahead, you go, wow, that must be, the mean has to stay the same, right? All we got to do is now find the standard deviation. Remember this, the standard deviation for the sampling, which is also called the standard error, is equal to standard deviation from the population divided by the square root of n. Okay, and so we're already in our calculator. We'll go 20 divided by square root of 3. That's all there is to it. 11.5455 if you round it. Yeah, so that's got to be it. So it's A, option A. And the key part is we learned how to use our calculator. We've got the answer key right here. I think we probably did pretty good. You could go back and check me. CCC is looking, I'm fairly pretty confident because of the calculator and its use. So anyway, that's the practice test. Study over those. Those are the concepts that we want you to be able to apply. That will help you as we go further and further into statistics and using it, applying it to make good decisions. All right. Thank you so much.